ReasonConf is brought to you by our gold sponsors Ahrefs and Chain Street.
Hey, good afternoon, everyone. Thanks for having me. My name is Douglas Teoh, and I work in Japan for a company called OLM. The company's focus is on developing mobile apps for the healthcare industry in Japan and other countries around the world. Some of these apps that we develop are in the process of getting certified as medical devices in Japan and the United States. When I was preparing for this talk, I did a little bit of research about software issues in medical devices. What I found was that, at least in the United States, the number of medical devices being recalled because of software issues has been growing over time. In fact, in recent years, software issues have become the leading category of recalls. I think that this trend is probably not that surprising because more services and products are being released with some form of software integration. Even outside the healthcare industry, the trend of adding mobile app or internet-enabled integration of products and services has continued to grow over time. Whether this software integration actually creates a better product is up for debate. Luckily, most of the time, the impact of software issues in everyday consumer products are fairly inconsequential. Some of these issues even get marked as first-world problems. But medical devices are one category where software issues have real consequences. Probably the most infamous medical device with a software disaster is the T-Rec25 machine, manufactured and used in the 80s. This machine is a computer-controlled radiation therapy machine. It had two operating modes, one for taking X-rays and another for destroying cancer cells with an electron beam. Both operating modes rely on controlled doses of radiation. Tragically, some patients found out the hard way that this machine had flaws, which led to the delivery of unintended doses of radiation. A commission to investigate why this had happened concluded that the primary reason was bad software design and development practices. Other issues such as bad user experience leading to operator complacency and also the manufacturer's dismissal of reported incidents ended up magnifying the consequences of underlying software issues. So this was a very serious and tragic disaster. What I want to talk today is about an app that we developed called FastDD. This is a mobile app for paramedics and other first responder personnel to assess patients displaying the symptoms of brain stroke. This app is nowhere near as dangerous as a radiation therapy machine, but it does have the power to affect lives. I want to tell you a little bit about brain stroke so that you have an idea of what it means. For those of you who don't know what stroke is, it is a medical condition where the brain has poor blood flow, either because there's not enough flow, also known as an ischemic stroke, or because it is bleeding, which is known as an hemorrhagic stroke. When there's not enough blood flow, brain cells don't get enough oxygen and brain cells start dying. When enough brain cells die in a particular part of the brain, whatever function that is associated with that part of the brain ends up getting degraded or lost. For example, a patient might not be able to move certain parts of their body or their speech might slur. So why would we want to write an app for this? For starters, stroke is one of the leading causes of death around the world. You do not have to be old to die from a stroke. Next, the symptoms of stroke can present itself over the course of hours. So this is something that we can reasonably observe and assess. This means that being able to assess the symptoms of stroke as quickly and accurately as possible increases the likelihood of patient survival. So how are these assessments carried out? The assessments make use of what is called a scale, and a scale is very much like a questionnaire. There are different stroke scales, and which one is used depends on what triage protocol paramedics in the region are trained to perform. Some scales are fairly simple in that the questions only require yes/no responses, while other more complex scales could have some form of data collection or branching conditions that depend on previous responses. The responses are used to generate an assessment where simpler scales just tally out the responses that show evidence of a stroke, while other more complex scales might also have to perform some calculations. The assessment is then used to triage the patient and determine the best hospital for the patient. Depending on the assessed severity of the stroke symptoms, hospitals with treatment capabilities or facilities appropriate for the patient are also recommended. Sending the patient to the right location in the first place is really important for the best outcome because not all hospitals are equipped identically. Transferring the patient to another hospital is wasted time, which means more loss of brain cells before treatment can start. Hopefully, you all have an idea now of why an app like this would be very useful for paramedics who are out there on the field. And to make sure that this tool is better than a pen and paper process and that the patient can get the best outcome possible, we want the app to be as reliable as possible. Last year, we rewrote the core of this app in ReasonML. The app that you can download today is running ReasonML code compiled with BuckleScript. It has been running ReasonML code for a few months now, so this is a real-world and in-production use of the language. So is JavaScript in an app that is aspiring to be a medical device a good idea? If you have written any amount of non-trivial JavaScript code, you probably already know that the language makes it very easy to write something that seems to work and then fails if errors like undefined is not a function or similar. These days, it is common to add linting tools like Flow and ESLint as a mitigation strategy. But these tools are not enough to guarantee that your program won't have runtime errors. The linting tools make use of metadata written around and external to the code and can only work if the metadata is written. This means that if we want our program to be checked completely, we need a tool where such metadata is written as part of the code. This means using a different programming language, usually one that supports compile time type inferencing and checking. There are quite a number of candidates to choose from, and we settle with ReasonML. For me, the advantages of ReasonML when compared against other mainstream compiled to JavaScript languages are the working type system, the availability of interrupt features, and the very fast compiler. Today, I want to share how some features of the language has helped us build a JavaScript component which is reliable in production. I will also share some details about how we integrated our ReasonML component into the app and prepared it for a production release. I'll start by showing where ReasonML fits into the mobile apps. Both the iOS and Android apps are written primarily using native code, Swift for iOS and Kotlin for Android. We have a backend GraphQL API server written in Ruby. The ReasonML component, which we call the engine, sits inside the mobile apps as a JavaScript component. In this configuration, the native code becomes a client of the engine. On iOS, the engine runs in Apple's JavaScript core engine. On Android, we use a third-party package called Liquid Core. In both cases, the code runs in an ES6-compatible environment. So what does the engine actually do? Well, the engine's main responsibility is to provide a common component which abstracts away how a scale is used by providing APIs for the client. This API includes instantiating a scale from data provided by the server API, defining a data format for what a question needs to render on screen and its UI behaviors, defining how question responses are exchanged between native code and ReasonML code, and defining a data format for assessments and recommendations. With this API, the client is mainly responsible for how the user interface is rendered, making API calls to the server, and integrating with OS services such as maps and geolocation. So now that you have an idea of how the app is structured, let's talk about some of the language features. Let's start with variants. At a superficial level, variants are like enums from other languages. The most common use case that variants share with enums is to model bit fields or similar kinds of flag attributes. But variants can do so much more than that, and I think that variants are the most powerful feature that you can use for modeling data and domain concepts. The payoff from this feature is incredible when you consider the simplicity of this language construct. Throughout this talk, you will see several ways in which variants end up shaping the code. The most common variant implementation in use is probably the option type. It is the most straightforward type to use when you need a way to model values that could be null. Everywhere that you use the option type, the compiler can check that you're handling the absence of values. This means that all the places where you could miss out on a runtime error is now a compile time check. You no longer need to keep in your head a mental map of what variables in your program could be null. And you no longer need to have defensive null checks everywhere. Not handling null is a very common source of runtime errors when working with JavaScript. So having a language feature which eliminates this entire class of errors raises the reliability of your programs. As I mentioned, one way that variants are useful is in modeling API data. our app receives stroke scale configuration data from the API. This data includes the questions and choices that we want to display. Each question and choice can have different behaviors in terms of how the UI is rendered and how user input is processed. To accomplish this, each question and choice object has a type attribute to indicate the desired rendering and processing behavior. When these objects are serialized by the API, each object has attributes for every possible question or choice type. Naturally, this means that each object, when deserializing, would also have a lot of attributes of null values. In ReasonML, we can of course model it directly as a reflection of what the API has serialized. This might mean a record type with many fields using the option type. The downside to this approach, apart from having to work with a lot of option fields, is that the domain knowledge is no longer represented in code. And this becomes a problem because now there's a temptation to rely on external knowledge like code comments and documentation, and then use unsafe operations like Belt's option module's getExtend function when accessing those fields. The end result is that we bypass the compiler's safety guarantees and reintroduce runtime errors into the system. The solution would be to model each question and choice type separately. This means that we no longer have to use the option type everywhere, and that we can safely use fields that are meant to be present without fear that we would trigger a runtime error. After modeling the question and choice types separately, we would still like to be able to pass around these records without having to write separate functions for each record type. The way to do this is to use a variant to unify the record types into a single type. Now, everywhere where we need to handle a question or choice record, the compiler can tell us if we did not write an implementation for a particular question or choice subtype. Let's look at one last example where variants have helped the compiler find domain errors. After processing the inputs for a question, there are operations that can be performed. One is to find the next question to display if there is one, and the other is to calculate the score for the question. If there are no inputs, then both operations cannot proceed. In both cases, we started off by using option types. This seemed to work, but eventually an issue was found in the automated tests when determining if a given sequence of inputs would produce a scale that finishes. The cause of this issue was that we ended up assigning multiple meanings to none. Why is this the case? Well, because we cannot have an unending sequence of questions to answer, at some point there will be no question. So this was initially represented by none. But we also said that the operations cannot proceed when the question is not yet answered, also represented by none. So this means that none has ambiguous meaning. The solution was to model these two cases using separate variants. One variant modeled the question's answer status, while the other variant modeled what the next step should be if the question was answered. After combining these two variants together, the compiler helpfully pointed out all the combinations to handle, which revealed the edge cases that were not considered. The lesson from this is to not use an option type if the none value is going to be meaningful in some way. The none value should only be used to indicate the absence of a value. If you want to convey some other meaning, you are better off creating your own variant to name all the cases or meanings that are relevant to your domain. Another useful feature in ReasonML is the ability to define interfaces for the purpose of hiding type implementations. String data is very common, and in our app, it is no different. We have strings for user interface labels, question and choice subtypes, and identifiers. We have already seen how strings that are used like enums can be modeled with variants. For our app, it is important for string identifiers to get some special treatment. When we compute the assessments, every scale requires some combination of questions and choice selections to be scored. This means that our code needs to reference these questions and choices with a known identifier determined ahead of time. If we just use the default string type, we could accidentally swap the use of question and choice identifiers around. This would be bad because it means that a correct result will most likely not be computed. In ReasonML, you can declare a new type in an interface without exposing the type's implementation. We made a module that made it easy to create these hidden string types. It also implements a few other functions so that we can use these types as map keys. Now, with these hidden types, it is impossible to use the wrong type of identifier. If you want to accomplish the same thing in other languages, you'll most likely have to write some kind of wrapper class or object. The great thing about ReasonML's implementation is that this functionality incurs no runtime performance penalty. All of this wrapping gets discarded away when the code is generated. So the code ends up working directly with the string values. After all questions are answered, we have to compute the assessments. The algorithms behind the assessments are translated into code from research papers. This translation has the potential to create bugs. When we try to compute the assessments, it would be great if we could either detect or report bugs that were encountered. The type of bugs that we were able to detect were mostly definition errors. I mentioned that we get scale data from the API. The assessments depend on questions and choices being both identifiable and able to produce the right type of outputs. For example, a button should produce a Boolean value. To report bugs that we detect, we use the belt library's result type. We mainly use this type as a defensive programming tool to make it easier to detect problems when developing the code. The result type is a parameterized variant used to encode the type of a successful result and the type of an error. The type of a successful result, in our case, at the end of all computations, is a record type. For the error type, this was reworked multiple times after reviewing the error handling strategy. Initially, error results were typed as strings, and in some cases, exceptions were raised. We refactored error string messages into variants, which has the effect of making it easy to see all the failure conditions that could be possible. After that, exceptions were replaced with error results, just because it didn't make sense for some failure conditions to use a different error reporting strategy. Using result types extensively did make using successful values more involved. We need to combine many results together. Some result computations were not dependent on any ordering. In these cases, we had code with several levels of nesting. To solve this particular issue, we had to implement multi-map and multi-flat map functions. If you want to use this solution, you need to be careful with the argument position and naming, since the computation expression is now decoupled from its name. Using result types makes it easy to implement a pattern called railway-oriented programming. This programming pattern identifies two computation paths: a success path seen on the top half of the diagram, and an error path seen on the bottom half of the diagram. The success path can generate either a success or an error, and the error path bypasses the computation of downstream success paths. This pattern is very useful when you need to implement the equivalent of an early function return, like in imperative programming. For us, detecting errors is very similar to doing validation in web requests. In both cases, when a problem is detected, we want to report the problem and return immediately. Implementing this pattern of result types is very much a case of chaining the flat map function in sequence. So after we write all that ReasonML code, we still need to somehow integrate it into the app. The concerns for interop are the issues you find when working at the boundaries between two programming languages. For our app, the practical concerns are how values and data structures get serialized and deserialized, and how functions on both sides of the boundary are invoked. In our app, JavaScript is used to bridge native code and code compiled by BakuScript. Serializing and deserializing values and data structures between native code and JavaScript is documented by the Liquid Core framework for Android and the JavaScript Core framework for iOS. For our app, we only exchange data structures containing data types supported by JSON. For the interop between ReasonML and JavaScript, BakuScript provides many strategies. I will just quickly summarize what we picked and why. For our app, each question screen has to communicate the user's inputs to the engine. The JavaScript API for this accepts an array of objects to accomplish this. In JavaScript, the type of an object's attribute can be anything, which works well for us because choices produce values whose type depends on the configuration. For example, floats for numeric inputs and booleans for buttons. To bind against this kind of polymorphic attribute, we use the JS module's JSON type. The module provides a classify function that is used to pattern match into more specific types. To support other functionality like the assessment screen and the hospital's recommendation, we have to bind to arrays and object structures and also create those structures. Unlike the question response inputs, we don't have values of polymorphic types, so this is much more straightforward. For binding JavaScript objects, we use the deriving abstract annotation. When generating JavaScript objects, we mainly use the BS-JSON library because the vast majority of types that we use are ReasonML types. So that covers the bindings. To get data flowing between ReasonML and native code, the JavaScript bridge layer exposes a public API to the client. The bridge layer also manages an instance of the engine and coordinates the overall data flow. Native code sends data through this public API. Native code receives data through asynchronous callback functions. These callback functions are injected into JavaScript's global scope. The bridge layer sends data back to the client using these callback functions. You might wonder why we use callback functions, and the reason is that the JavaScript environment is running on a separate thread, so we don't want the user interface to block while the engine is processing. So using callback functions allows the bridge to return results asynchronously. This overall data flow is a little bit like a game loop. Such an important component of the app will need to be tested. Automated testing is something that we were able to improve as a result of reworking the call functionality into a standalone engine. We implement automated tests using the BS-JS library. We have unit tests for individual modules and integration tests for each scale. The integration tests deliver the most value because for each scale, we get to simulate user responses, check how the scale evaluates each question, and check the expected assessment results. The result types that I discussed earlier made it a lot easier to detect issues. Integration testing used to be a very time-consuming manual process by the QA team, so having these automated tests freed up a lot of time. The integration tests also made refactoring much safer because it was immediately obvious when a change ends up breaking expected functionality. Finally, we are at the end of the development process. To ship the engine code to the client apps, we compile everything into a single JavaScript file. We use Parcel to do this because it is the simplest tool to accomplish this. The apps just ship the compiled file as a static resource. In the beginning, I mentioned that we are in the process of getting our apps certified as medical devices. To try our best to avoid becoming a part of the medical device recall statistics, we need to write the most reliable app possible. ReasonML is one of the tools that we hope will continue to help us achieve reliability. The title of my talk is Saving Lives with ReasonML. While I would have liked to show you that the language has an epic feature that made ReasonML the only viable language for saving lives, what I showed today was what I think are conceptually simple features. Variants, interfaces, and result types were combined together to create a program that is a lot more provably reliable. I don't think that we would have been able to achieve the same reliability if we used a mainstream alternative like TypeScript. I think that writing this in standard JavaScript would have been foolish. So far, we have not seen any crashes because of our ReasonML component, and we hope that it will continue to stay that way. Saving lives is a very ambitious goal, and I feel very lucky that I could contribute towards this universal ideal. If you are still unconvinced by ReasonML, I hope that you would give it another chance. Some people out there have already had their lives saved by this, even if they don't know it. Thank you.